Hello everyone, my name is Wenkai Li. I'm a first year PhD student at Hainan University. It's my privilege to represent our team and talk about our work, COBRA interaction with Bytecode-Level vulnerability detector for smart contracts. This work is jointly done by Zhongwei Li, my supervisor, Professor Xiaoqi Li, Professor Yuxin Zhang, and myself. Ethereum is one of the most popular blockchains, which supports the development of smart contracts. However, lots of security events happen on the Ethereum due to the defects of the smart contracts. Therefore, to protect smart contracts from being attacked, a lot of vulnerability detectors have been presented. They use several techniques such as the symbolic execution, and flooding test to extract semantic patterns of malware behaviors. Then the extracted results can be used as classification of smart contracts. As for the symbolic execution, the tools focus on the execution flow of the contracts, validating the path visibility on the operation code level, what we call the semantic perspective. Regarding to the fuzzing test, the technique inputs random values according to the function interfaces and monitor the program's exception to find vulnerabilities. However, they both have corresponding advantages and disadvantages. The symbolic execution finds all the passes, so it's effective, but it's slow. The fuzzing technique tests parts of inputs, so it's fast but not that effective. So to reconcile them, we consider the function interface as a factor, getting the semantic features and try to get more effective and less time consumption. Thus, the question comes out, how can we detect the vulnerabilities of smart contracts with the above features? To resolve the problem that combine the two features, there are two challenges. The first is the scarcity of the public function interfaces. Function interfaces can be divided into API and function signatures. According to our statistics, only parts of the API and the function signatures are public. Therefore, how to effectively open uh, obtain this data is a problem we need to solve. The second is security of the open source contracts. Our research object is the smart contracts, but according to our statistics, only about 1.79% of them are open source. So we need to focus on the Bytecode smart contracts to resolve the above challenges. We propose our framework called COBRA. The COBRA has two steps. The first one is the signature reverse inference from the function, short for Swift. The contract translates the function interfaces into encrypted byte form and compile time. But what we need to do is infer the function interfaces from the byte form function signature. So it's a bit of a reverse engineering. The second, the function interfaces and the semantic features are combined to infer the vulnerability categories existing in the contract. For the first component, which is the Swift, we first convert the bytecode contract into a control flow graph, and then use OP codes such as the jump and the jump disk to determine the function blocks on it. After dividing the contract into multiple function blocks, we input the function blocks into Swift, and the corresponding function parameters can be obtained. This is a classic sequence-to-sequence structure. We first translate the function bytecodes in the sequence of operation instructions with operands. Then its feature is obtained by the LSTM. And the attention mechanism optimizes the model outputs by considering the relevant weights of the hidden layer vector units in the decoder at each step. Finally, we utilize LSTM as a decoder to gather results. In addition to the parameters, another important piece of data in the function header is, a, is the function properties. To obtain the function properties, we summarize a table of contrast relations. By looking for the existing of the corresponding opcode in the function, we can infer the existing of the corresponding properties. The resulting properties, together with the function parameters, can be used as part of the function signature. For the second part, COBRA incorporates function interfaces and the semantic features for vulnerability detection. COBRA also has two components of feature extraction, namely semantic features and interfaces features. For, for the acquisition of semantic features, we transform the contract bytecode into the SSF form. It's a intermediate expression form, and we fed the SSA from opcodes into the ByGRU layer to obtain the semantic features. For the function interface features, we use the results obtained in Swift with the polling and the CNN layer to obtain the corresponding feature vectors and align their dimensions. Next, by concatenating the two features together, we can obtain a new contract feature embedding. Finally, we can perform vulnerability classification by assessing a decoder. The next part is our experimental evolution. We utilize to celebrate the dataset for tool evolution. For the vulnerability detection, we collect some bad codes from the exploit student and we label it through the smart bus. And as for the signature inference, we extract 3,000 samples from the exploit insertion dataset, and each sample is then used for collecting the function signatures in 4 bytes. Finally, we obtain, obtain around 99,000 function signatures. We firstly see signature inference task. In this task, Swift can achieve highest performance when an LSTM is used and the function-based block depth is 1. Moreover, it can obtain a FE score of nearly 94% in the testing. Furthermore, when comparing with other state-of-art, we find that we can also have better inference rates. Note that the inference is considered successful only if the order and number of the function parameters are correct. Then, for the vulnerability detection task, COBRA achieves the highest performance when using GRU and focal loss and achieve a FE score of 93% in the testing. Comparing to other state-of-the-art, we can able to achieve the base FE score. Note that my3 is the symbolic execution tool. We test each contract with a timeout of 30 minutes to see if function interfaces are actually beneficial for vulnerability detection. We conduct an evaluation experiment. In this evaluation, we can see a significant improvement in the performance with the API. And when we only have function signatures, we introduce a MACAM structure, which give us a recall almost 90%, 90 percentage. Finally, we also conducted a series of tests on the contracts in the wild, and we found two new zero-day vulnerabilities. Therefore, in conclusion, COBRA supports both function signature inference and bytecode level vulnerability detection. Thank you for your listening.